Greetings, fellow mathematicians. This is quiz number 2 for my Calculus 2 course covering area between curves. If you want to make an attempt at this, pause the video and give yourself about 10 minutes. And when you're ready, we'll get to problem number 1. Let's start this first problem by drawing a simple sketch of the region. If we take a look at the first two curves, y equals x squared plus 3, that's going to be a basic parabola, shifted up 3 units. And y equals negative 2/3 x plus 2 will be a straight line. So let's sketch the first curve. Take your basic parabola and we're going to shift it up 3 units. And if you take a look at your other two equations at the end there, x equals 0 and x equals 3, those are equations of vertical lines. They're positive. We don't have to really worry about the curves being within the positive x-axis. So if we go ahead and draw just the one side here, get a quick rough sketch of x squared plus 3. If we take a look at the other line, y equals negative 2/3 x plus 2, that has a y-intercept of 2, and the slope, the number multiplying x, is negative 2/3. So we're going to go from the y-intercept, we're going to go down 2 units and over 3. All right, and the last two curves there, x equals 0 and x equals 3, those are equations of vertical lines. So we have that one right there, and that one right there. So let's label everything. We have this as x equals 3. We have that as x equals 0. And this curve on the bottom, negative 2/3 x plus 2. So our region in question that's bounded by all of these curves is that right there. And with your sketch, you'll be able to easily determine what the upper function is. The equation for the upper curve, that's x squared plus 3. And the equation for the lower curve is negative 2/3 x plus 2. With the equations for the upper and lower functions determined, we can now easily set up the integral that calculates the area between these curves. Just be careful and use this tip here of using parentheses around y lower, since you're subtracting several terms. So if we simplify, we have our integral from 0 to 3 of x squared plus 3. Distribute that negative, you'll get plus 2/3 x, but now minus 2. And you can go ahead and combine the like terms, the numbers there, 3 and negative 2, and write this as the integral from 0 to 3 of x squared plus 2/3 x plus 1. And at that point, we can now find an antiderivative term by term by applying the power rule. If we go ahead and do that, we'll get for the first term your antiderivative for x squared. That antiderivative will be 1/3 x cubed. The next term, think of the 2/3 as a constant multiple, and we're going to look at x as being x to the first power. So the power rule would give us your antiderivative 1/2 x squared. And be careful with your antiderivative for 1, that would become x. And the last step, we're going to evaluate that from x equals 0 to x equals 3 with the fundamental theorem of calculus. Now before you plug in there, notice you can cancel out a factor of 2 there and clean that up a little bit, which will make the evaluation of the last two steps there, plugging in x equals 3 and x equals 0 and subtracting, a little bit easier. So if we write this out, our simplified antiderivative is 1/3 x cubed. We have now plus 1/3 x squared plus x, and we're going to evaluate that at x equals 0 and x equals 3. The nice thing about this having a lower limit of x equals 0 for the integral, evaluate all three of those terms at x equals 0, they all become 0. So if you plug in everything here for x equals 3, you have 1/3 times 3 cubed plus 1/3 times 3 squared plus 3. And with a little bit of work, you can go ahead and show that that simplifies all to 15. And that would be the area of the region bounded by those curves. Let's go ahead and get to problem number 2. For problem 2, let's start by noticing each of the curves are parabolas there. The first one, 1/2 x squared, that's your standard parabola centered at the origin, but it opens a little bit wider. So let's go ahead and draw that. Just a quick rough sketch. That'd be your graph of 1/2 x squared. And to easily sketch the other parabola, y equals negative x squared plus 9x, we know that's going to open down, but we can easily graph it by first finding the x-intercepts. So we're going to set y equal to 0, and we get this simple equation, 0 equals negative x squared plus 9x, and we can solve that by factoring. You can factor out a common factor of x, and you'll get as your factorization x times negative x plus 9. And at that point, we can set each factor to 0. We get x equals 0 from the first one. And our second equation, negative x plus 9 equals 0. That's going to imply that x equals 9. All right, so we know this other parabola, it's going to cross the x-axis at 0 and 9, and it's going to open down. So if we draw a quick sketch of that, would look roughly like that. So that's your graph of negative x squared plus 9x. And we have a region bounded by those curves. You can see you get an intersection point up there, which we'll calculate momentarily. But the region in question is this right here. To find the intersection points, we're going to set the two functions equal to one another. So we end up solving this equation, 1/2 x squared equals negative x squared plus 9x. And that's a basic quadratic equation. I'm going to put all the terms on the left side. That way we have a positive coefficient for x squared. So add 1 x squared to each side. You'll get 3/2 x squared. And then subtract 9x. And we get minus 9x equals 0. And you can actually solve that by factoring. You can factor out a greatest common factor of 3x, and you're left with, in parentheses, 1/2 x minus 3. And from there, we can set each factor to 0. We get a simple equation here, 3x equals 0. That implies x equals 0. That might be obvious from your sketch. X equals 0 is that leftmost intersection point, which does look like it's the origin with x equals 0. And the other equation, that's going to give us the rightmost intersection point. And that's going to be really easy to solve if we isolate x, so add 3 to each side. And then multiply by 2. And it looks like we get that rightmost intersection point. That's going to come out to be 6. And that'll be how we set up our integral. Our integral for the area between these two curves will go from x equals 0 to x equals 6. Using our sketch, we can determine that the equation for the upper curve is given by y equals negative x squared plus 9x, and the equation for the lower curve is given by y equals 1/2 x squared. Our integral to calculate the area is going to go from the intersection point 0 to the other intersection point 6. So we get our integral here going from 0 to 6. of the upper curve minus the lower curve. Now we can go ahead and simplify some of those terms there. We can combine negative x squared and negative 1/2 x squared to give negative 3/2 x squared. And then we have just plus 9x by itself. And at that point, we can now easily find an antiderivative term by term by applying the power rule. So the first term, we're going to think of negative 3/2 as a constant multiple. Your antiderivative for x squared would be 1/3 x cubed. And the second term, think of 9 as a constant multiple, and your antiderivative for x is 1/2 x squared. And the last step there is we would evaluate that from x equals 0 to x equals 6. Now before you do that, notice you can clean up the factors there. You can cancel out those factors of 3 and write your simplified antiderivative as minus 1/2 x cubed plus 9/2 x squared, and we're going to evaluate that from x equals 0 to x equals 6. Now the nice thing about the lower limit being 0, both those powers of x evaluate to 0, which means the only part that survives after we plug in the limits from the fundamental theorem of calculus is the part when we plug in x equals 6. So what we get here is minus 1/2 times 6 cubed plus 9/2 times 6 squared. And if you work through that, you can show that you get as your area, that comes out to 54. And that is it for quiz 2. If you found this helpful, support the channel, like and subscribe.